We want to know that, of course, without doing anything, just by releasing this bar or this pendulum from its current position, gravity will pull this thing going downward, just like the example I mentioned before, right? Therefore, there's going to be an angular motion in this problem, for sure. And from here, you also know that it's going to be constrained motion, because the center of gravity is not the center of rotation. This has been constrained. Now, we want to find out what is the angular velocity. What is angular velocity if I applied a moment? And this moment has a magnitude of 30 Newton meter. Suppose I apply the moment to the whole pendulum, and this pendulum is going to spin to this point. It's going to move. So initially, the omega is 0, correct? We assume that the problem starts from rest. So initially, there's no angular velocity. But when this pendulum, upon the application of the moment and also the application of gravity, is going to move going downward. And the question is this: what is the angular velocity when this pendulum is at 90 degrees? That means from here, from its original position to the vertical position when it's theta is 90 degrees. We want to find out what is the angular velocity. That's what we want to know for this problem. Okay. So let's solve the problem. Now to do this, of course, we know that we got to figure out that what is the mass moment of inertia at the center of rotation. And the points I defined here, I said this point is A. So the center of rotation is called A. And this point is B. So this is A, this is B. We have two different objects. Let's find out the mass moment of inertia at point A. So what is the mass moment of inertia at point A? For the bar, if you remember the result we derived before, at the end of the bar, the mass moment of inertia is already determined to be 1/3 of the mass of the bar times the length of the bar squared. Right? That's what we did from last example. For the bar, we already know it. So that's not. This is already the result from parallel axis theory. So you don't have to add anything. It's already 1/3. Because at the center of the bar is 1/12. And then we have to add the other term, which is this guy. And now for this guy, we really need two terms. The first one is at the center of gravity, which is at the center of the disk. And that is 1/2 of the mass of the disk times the radius of the disk. And the radius of disk, which is 0.8 divided by 2 squared. So this is the mass moment of inertia at the center of gravity for the disk. And then you have to project it. The mass of the disk, of course, we know it is 10 kilograms. You have to project it from the center of gravity to the center of rotation. So this will be the second term. That is md times d squared. And what is the distance here? What's the distance from the center of gravity of the disk to the center of rotation in this problem? That's going to be 2 plus 0.8 divided by 4. So that's 2 plus 0.4, correct? So here it is 2 plus 0.4 squared. And that's this result. We already know MB is 10. What's LB? That's the length of the bar, which is 2 meters. So MB is just 3 kilogram, and D is 10 kilogram. So we have everything we know, and this value I will just give you here is 62.4 kilogram meter squared. So this is step 1. We found the mass moment of inertia at the center of gravity. Now, we want to put all this together. To use the principle of work and energy, or to consider this, we have to recognize that there are 2 different things. Just like what we did before, we call the principle of work and energy the summation of the kinetic energy and potential energy. I use we're going to use T1 and T2. I think this may be easier. T1 plus the summation of total work from 1 to 2 equals to the summation of kinetic energy at T2 plus the potential energy at T2. Remember? This is what we learned from work and energy. Now, before you carry out any further calculations, ask yourself this. This term is what we call total work, right? And the work can only be produced by what? First, external force, right? Do we have external force here?
Gravity?
Gravity is not external force. Gravity goes to the potential energy. Do we have external force here?
No.
What about this?
Yes.
We do. So here, external force. Do we have it? Yes. It's not force, but it's external moment. It's external. We don't know why it's 30 Newton meter, right? We don't know why. Because it's external. So we do have external moment. And what else? What we call non-conservative forces, right? Which is what? Friction. Remember? Or third, cable force. If you put a cable there, you have to consider that, put it into here. Calculate the work produced by the cable force, right? If you have a friction, you also have to consider the frictional force. Put it here. Otherwise, everything else, what about the spring force? Spring force goes to potential energy. We call it as elastic potential energy. Gravity goes to potential energy. We call it gravitational potential energy. So that's why the step 1 is always to check what are the terms you're going to go into this work calculation, which is only this one, external moment. We don't have friction and we don't have cable. It's only this. So you're going to have a non-zero work. That means you have to calculate the work here, and you have to calculate kinetic energy. You also have to calculate potential energy, because in this problem, the center of gravity will experience vertical displacement. That means there's a change of potential energy. If you set this to be the datum line, this line, and that's the center of gravity for the bar and also for the disk. They are all at the datum line. But when it rotates to 90 degrees, they will experience different levels of vertical displacement. Okay? And we will solve the problem after the exam, which is next week. Any questions? Any questions?
Nope. Thank you.
All right. Okay. I will see you on Friday. All right.